Still talking about modern topics in stochastic processes. This video is about Monte Carlo simulation. Monte Carlo simulation. I know we've seen it somewhere. I think we talked about, there was a video about MCMC, that's Monte Carlo Markov chains. So talking about Monte Carlo simulation now, the concept and intuition, first, Monte Carlo simulation is a method of solving problems using random sampling. So we solve problems using random sampling. The core idea is that if a problem is too complex to solve analytically, we can simulate it many times and approximate the results. So if you cannot solve a problem so easily, like there's no closed form solution which you can evaluate, you can then take, simulate and record values and then take the average at the end of the day, approximate at the end of the day. So the mathematical foundation is that if you let x be a random variable, so the expected value of f of x is approximately 1 over n summation from I equals 1 to n of f of x sub I, where x sub I are random samples and n is the number of simulations. So here now we need to estimate pi. Now we use pi, we estimate pi using geometry. So now, what it's more like we want to use the concept of Monte Carlo simulation to estimate pi. Pi is a very popular, it's a very popular value in mathematics, right? It is connected with cycles with circles rather, I mean. So we estimate pi using geometry. So pi is approximately 4 times the points inside a circle and the total points. Okay, so we randomly generate points in the unit square and check whether they fall inside a quarter circle like that. So, and to pull up the mathematics, right, we have this expression right here. Okay, this is going to take a lot of time, but before now I had done this. So if this happens again, we are going to have to, the shape might shift, right? And what is the code telling us? So we want to use Monte Carlo simulation to evaluate the value of pi. Oh, this is fast this time around. Interesting. Okay, so we have that. So define Monte Carlo pi. The number of samples, you have 5,000. You can take more samples if you like. So you have x random samples, y random samples, and inside you have x squared plus y squared less than or equal to 1. That's the equation of a circle functionally. So then you can then plot the scatter values of x inside and value of y inside. Then you plot value of x not inside and value of y not inside, and you do the Monte Carlo estimation of pi using that idea, and it returns 4 times the mean of the points inside. So, and then estimated pi can then give you the Monte Carlo pi, which we have down here. That's 3.136. Of course, you know pi is roughly 22 over 7 or 3.142, blah blah blah, right? So, if I keep running this, it keeps changing, right? Um, it keeps shifting a little bit. So this is a square. This is a one by one square, right? That's 1 times 1. That's a square unit. So and then we have and we define the circle, right? So this is a quarter circle like that. So, and we estimate pi based on that. And the estimation, this one is 3.1296. If you do it again, it's 3.1432, So you can see it's hovering around the actual value of pi, 3.14, 3.15, 3.15 again, and so on and so forth. So we can use Monte Carlo simulation to get, of course, there's no particular formula to estimate pi, to get actual value of pi. So the best we can do is estimate, right? There are all kinds of formulas here and there to just estimate. So Monte Carlo is another way another approach. So let's talk about convergence theory. And that brings to remembrance some concepts we had considered previously, even popular concepts in statistics and probability. So Monte Carlo relies on the law of large numbers, that it's more like the more inputs you have, the more data points you have, the better results you're going to get, right? So to speak. So Monte Carlo relies on the law of large numbers, which is that 1 over n summation xi approaches the expected value of x. So it means that the more points you have, the closer you get to so it's more like you have a population mean and a sample mean. The more samples you get, the closer your estimation of the sample mean gets to the actual population mean. So that's the fundamental idea there. So as n increases, the estimate becomes more and more accurate. So if I imagine now, if I do this, if I take just 500 samples here, we took 5,000 samples here. If I take 500 samples here, so yeah, see the estimation. I mean, we got a result. Oh, in fact, we still get something like 1.36, but you can see that it's not that reliable, right? Or let me even do 50 samples. That would be worse off, I suspect. But you know, so now you see the estimated value of pi is 2.96 because I have fewer points to estimate it. So by the time I get to like, let me go to 100 and see how well 100 behaves here. So for 100, 3.2, okay, getting better. Then we now go to that 500 now. So at 500, it's already close to it. So if you want to have, okay, I mean, even this 500 is giving 2.99, but of course, as you keep running, it gets, okay, now this is 3.2. So uh, the more samples you get now, the closer you get to the actual value of that pi. So you see this one now is 3.1184. So, and if you keep running this, it keeps hovering around that 3.14 kind of thing. So let me see if I can do 50,000 and it won't waste time. Let's see. So 50,000. Okay, so you can see things are smoothing out already. And that, so you can see the 3.14 is coming out perfectly now. So 3.14, 3.15. So just hovering around that value. 3.15 again. So let me push my luck and see if I can do 500,000 samples. Okay, I know that's gonna, yeah, and it's, wow, it does it. So you can see the estimation is getting closer and closer. The more samples I have, this is now like 3.1416. So that's basically the idea of the law of large numbers, right? So the more input you get, the closer you get to whatever it is you might be estimating, like that. So that's the idea. So that's the convergence theory thing. So as n increases, the estimate becomes more accurate, basically. So, and here talking about the convergence of pi now. So, we've estimated pi up here now. We now want to talk about the convergence of pi. So you can see that so when you're at zero, it's like up there. So you are getting like 4.0 or something. But as you keep moving, getting more and more samples, so you still have a kind of movement above the actual value of pi is this line you have it at 3.142, blah blah blah, like that. So, but as this number of samples are increasing, the things are aligning, get better and better. I mean, the whatever the estimation you're getting is getting very to closer and closer rather to the actual value of pi. And that's the idea of the convergence theory. And I was able to demonstrate that here for you to see. So, and the more points you have, the smoother the circle gets, as we saw the other time, right? Like when I did 500,000. So now you see, you can still see the points. So when you had just 50 points, you could see the points like scattered all over the place, but now it's getting smoother and smoother. So what if I do 1 million? I'll just like to push, push, push 1 million. Yeah. So that's going to take a bit of time, but of course, you're going to get almost like a perfect, like everywhere is just smoothing out like that. So that's the kind of thing we're talking about with this here. So let me take it back to the 5,000. Oh, no, it's 50,000. No, no, no worries. Yeah. Let's do the 5,000 thing. Yeah, that now. Okay, so we see convergence theory there. Then we talk about Monte Carlo integration. Monte Carlo integration, we approximate uh, i- s- uh, integral of x squared dx from 0 to 1. Of course, when we do that, we know we're going to get 1 over 3. So using Monte Carlo estimate, now we do integral from a to b, integral of f of x dx from a to b. That's like b minus a, 1 over n summation f of xi. So it's like you're going to cut okay, well, if we use like Desmos, you know how that happens. Uh, Talking about Desmos, and then you integrate x, right? Is it x squared? Yeah, integrate x squared from 0 to 1, you get 1 over 3, right? So it's more like so normally when we integrate x squared, right, we get 1 over 3 x cube, that'll be 1 over 3 x cube. So so imagine you have 1 over 3 x raised to power 3. Okay, and that is now limited between So is it a comma we need here? So you now have, okay, I think, how does that work again? Yeah, I think it's like this. So you now have 0 less than or equal to uh x less than or equal to 1. So it is within that simple range now. So what we are doing now, it's like we are taking the area under this graph, as you can see. So it's more like when we take the area under this curve now, uh, oh, the line is off. I'm trying to see if we can shade this. What can I do? Let's see. What can I do here? So you have, let me see if I can do 1 over 3, 1 divided by 3, x cube, x raised to power 3, right? Less than, less than 0. Okay, that's not working. Less than, okay, less than 0. No. What can I do with this? The value of x, right? So, okay, let me try an experiment with this. I'm not sure. I just want to see what I can get to do with this. Less than or equal to this, less than or equal to, less than or equal to 1. Okay, that's not doing anything. Uh, okay. But shoot, less than or equal to 1. Not working. Okay. So, in short, what I'm just trying to say is that with this now, for the Monte Carlo simulation, what we are just trying to now do is, you have that curve there, you have this curve, and then this just goes up a bit. That's not too smooth. Just try. So, what we are doing now is under this region now, this is 0 and 1. So you now break it into very tiny, very, very many tiny strips. The more of the strips you have, the finer the strips are, the better your estimation of the area, which you already know to be 1 over 3, right? So um that's exactly what is happening here. So the basic idea of Monte Carlo is that you do something several times, and the more points you get, the better the results you get. So once we estimate this 1 over 3 now using this expression, which looks more like trapezoidal or one of those quadrature methods. So, and that's what exactly you have here. So you have Monte Carlo integration. Okay, I always like this. I always like this to be like in LaTeX. This is X here. So I put dollar signs around it. So if I run that now, it comes out more beautifully here, like that. So here now we have so if you look at the code, we have 5,000 samples, and then we do the kind of thing we did the other time to estimate the area under the curve. That's now you see the area now is this blue region. That's the area under the curve now, which we are looking for. So, and that's like 1 over 3 is 0.3333. This one is given as 0.339. Not a bad estimate, by the way. So imagine if I now make this, okay, so, okay, now we have this. So what if I make it like 5,000, 50,000 samples following the law of large numbers? So we get something finer, okay? And then you can see this is now closer. The other one was 0.339 or something. So now it's closer because the actual value of 1 over 3 is 0.3333. So the more samples we have now, the closer we are getting. So what if I do 500 samples only? So we get a bit removed from the reality. So this is 0.338, whereas we need to be 0.33333. So if you have more samples, you get better results. So this is like 500,000 samples. And then, of course, you can always be sure we are going to get 0.33. Okay, now 0.33606 and so on and so forth. And you can see it's really smooth now. So that's the way that goes. So but of course, we are using something we know, like we can easily integrate x squared to get between from 0 to 1, we get 1 over 3. But so we use something we know like that to establish the fact that, oh, this actually works. So when you now do it with something you don't know, you can be sure you are doing the right thing. So random sampling, Monte Carlo depends on proper random sampling. So, and if you have a uniform distribution example like we have here, so you have samples, you sample 10,000 random samples, right? And then you want to plot the figure. So you have uniform distribution, you have the samples, these 10,000 samples and the bins. You want the bins to be 50, and then value. So you have the value against the frequency. So of course, this has to keep changing because it's all random, right? So as you keep running, it keeps changing because you're taking random points like that. Okay, so then let's talk about application in option pricing. That's of course financial. That's in finance now. So application in option pricing, we estimate the price of a European call option, which is C equals 0 per minus RT, which expected value max ST minus K, comma 0, where S sub T is the simulated feature price and K is the strike price. So I know my quant friends will understand all these things clearly, or people that work, in the finance sector, like stock markets and all of those financial markets like that. So they define Monte Carlo option with S naught, that's initial price to be 100, K is 100, T is 1, and all these things. And then you define the formula here, and then that's this particular formula we have here. So, and then we we put everything together and we return. Okay, this is where the actual return is happening. But because it's random, right? This also will have to keep shifting like that. Yeah. So it keeps going that way. Then we talk about error behavior. Monte Carlo error decreases as error approaches 1 over square root of n. So already, so it means that as n, if n approaches infinity, the error almost goes to 0 because the error is decreasing with as the number of samples are increasing. So because the higher the number of samples you have, the more accurate your result would be. And the more accurate your result is, the smaller your error would be. So Monte Carlo error decreases as error approaches 1 over square root of n. This means increasing accuracy is computationally expensive. So if you want accuracy, you need so many sample points like that. So, and here this this code here gives us the error decay, shows us how error, you start with a very large error, and over time the error then gets as close as possible to 0 like that. So that's the error decay right there. Then we have variance reduction. So techniques to improve efficiency, you have things like antithetic variates, control variates, and importance sampling. So, and we have that here for the case of the circle, right? We have that like that. And so the improved pi based on this time is like 2.0. Of course, we know pi is 3.142 and all of that. Okay, so this is antithetic pi in this case now. So then we have multi-dimensional Monte Carlo. So you can have Monte Carlo in 2D, 3D, and so on and so forth. But here, this is multi-dimensional Monte Carlo. So you have an example. You have double integral from 0 to 1 of x squared plus y squared dx dy. And then we can easily do that here. So define Monte Carlo, take the number of samples you want. It's all about sampling with Monte Carlo and estimating, approximating. So you have X, you have N random samples, Y, N samples, and you are returning the average, the mean of X squared plus Y squared, over the samples. And you don't forget that, of course, normally we can solve this and know what the result is. I don't know, should I go for that? I think I want to do that. I've not solved some maths in a while. So let's do that. So yeah, I'll just go for that. And then so we can actually know what we are estimating for. So we have integral from 0 to 1, integral from 0 to 1, x squared plus y squared dx dy. Okay, now the estimate for this is, well, for me, like I like to indicate which is which. So this is, of course, they are both the same, so it's easy to just take anyone. So let's just say x equals 0 to 1 because we have a 2D situation here now. So what I like to do first, I want to take care of the dx first. So that's integral from y equals 0 to 1, then integral. So it's like an also integral from x equals 0 to 1 of x squared plus y squared dx, and I take the dy outside. So I can deal with x first. So in this case, I then have integral from y equals 0 to 1 of, so when you integrate this with respect to x now, because the focus is on x now, so when you integrate x squared with respect to x, you get 1 over 3 x cubed. That's x cubed divided by 3. Then when you integrate y squared with respect to x, that will simply be, so y squared is like a constant now, that'll be y squared x now. Okay, y squared x now you have integrated, so it's now going to be from x. You see why I like to write x, the parameter, so that I'll know what I'm fixing and what I'm not fixing. So now I know I'm dealing with x there. So, and then you have your dy right here. So, and then we move on to evaluate that further. So you have integral from y equals 0 to 1 of, so if you then substitute, okay, well, I like to split things up a little bit. So I can say this is 1 over 3 x cubed from x equals 0 to 1 plus y squared x from x equals 0 to 1. So all this now dy. Okay, so I want to get the actual value so that when we are estimating, you know what we're estimating for. So integral now from y equals 0 to 1 of, so you now have 1 over 3, 1 over 3 into, so when you put 1 for x, you have 1 cube minus 0 cube easily plus y squared into 1 minus 0 because of this x now. So all that dy. And then we move on and we then have 1 over, okay, we then have integral from y equals 0 to 1 of 1 over 3. 1 cube is 1, 0 cube is 0 plus y squared. 1 minus 0 is 1. All of that dy like that. So then we have that to be integral from, so now we don't have to worry again. Everything is now y. So I can just say 0 to 1 of 1 over 3 plus y squared dy. Okay, 1 over 3 plus y squared dy. So now we can then say that's integral from 0 to 1, 1 over 3 dy plus integral from 0 to 1, y squared dy. So this is more or less like 1 over 3 integral from 0 to 1 dy plus integral from 0 to 1 y squared dy. So we can then do justice to this now. This is 1 over 3, integrate dy, you get y, and that's y from 0 to 1 plus integrate this, you have y cube over 3 from 0 to 1. Okay, so that's 1 over 3, y from 0 to 1 plus, you can take out, I like to take out the constants usually. So that's also 1 over 3 y cube from 0 to 1. So that means I have 1 over 3. So when you put 1, that's 1 minus 0 plus 1 over 3 y cube, that's 1 cube minus 0 cube. Okay, so that is 1 over 3 into 1 plus 1 over 3 into 1 cube is 1 minus 0, that's 1. So everything ends up being 2 over 3. So we can conclude that therefore integral from 0 to 1, integral from 0 to 1, x squared plus y squared dx dy is actually 2 over 3. And 2 over 3 is approximately 0.666667, like that. Okay, so that's what we are basically estimating. When you use Monte Carlo, you want to get as close to that as possible. So with 10,000 samples, we get 0.6633, like that. So if I run it again, like 0.666152, 0.66886. So that's for 10,000 samples. What if I do 100,000 samples now? So you see it's getting closer to the 0.666. What if I do 1 million samples? So that's 0.6666. Can I do 10 million? I hope that's not going to waste time. Yeah. So yeah, like that. So the more samples you get, so it's giving us some approximation that can be sort of reliable. Then we can have you can do a mini project on a 3D sphere. So this is like a sphere x squared plus y squared plus z squared less than 1 now. So this is like a sphere with radius 1, or with I mean, you're talking about inside of a sphere now, inside of a sphere. That's what this expression is about. So you can define Monte Carlo sphere with 100,000 samples. So in this case, now it's three-dimensional. So NP random uniform, you know, like, okay, not quite like what we did before, but this is necessary. Random uniform, blah, blah. And then you have all of this less than or equal to 1. And then you do probability that you have a point inside the sphere, So probability inside the sphere, that's 0.52322, like that. So that's the deal for that. In summary, we see that Monte Carlo, Monte Carlo simulation uses random sampling to approximate solutions, and it converges as one over square root of n. So it means the larger the samples, the smaller the the error. Then it works well in high dimensions. Then the key idea is that Monte Carlo is equal to random sampling plus averaging. So you sample as many times as possible and you average out what you have sampled. And that's very good if you are not able to get a closed form solution to a problem and you just want to estimate. So the strengths of Monte Carlo include that it is flexible and easy to implement, and the weaknesses include things like slow convergence and it requires many samples. So if you want to get as many reliable answers as you want, you need it is computationally expensive, like they say. So you need so many points, you need compute power, and it takes a bit of time. So that's the idea of that. So the practice problems, you have conceptual questions like this. Explain the core idea behind Monte Carlo simulation in your own words. Why does Monte Carlo simulation rely on randomness instead of deterministic computation? Then state the law of large numbers and explain its role in Monte Carlo methods. What is the relationship between sample size n and estimation error? We talked about all of that. Why is Monte Carlo particularly useful in high dimensional problems? Okay, because high dimensional, the higher the dimension of a problem, the more complicated it becomes for you to solve. So by using Monte Carlo, you can take several samples, and then you approximate, you average them. So basic applications, you can write a Monte Carlo method to estimate by using random sampling. We did that already. Modify the pi estimation method to track how the estimate evolves over time. Then you want to estimate the integral. So you can integrate this and know the value. Then you can now use Monte Carlo to simulate and see how well it's getting. Then you can also estimate sine x dx from 0 to 2. Then use Monte Carlo to estimate the area under f of x equals e raised to minus x squared, you know. Then you have it in probability and geometry too. Estimate the probability that a randomly chosen point in a unit square lies inside the circle of radius 1. That was the kind of thing we did before. And then you want to estimate things like x squared plus y squared less than 0.5. That is that a point lies within a circle. That's what this simply means, you know. Extend to 3D, you can have the same thing here, like a point lies within a sphere. Then you want to estimate the volume of a sphere using Monte Carlo sampling. Then, of course, you know the volume of a sphere is 4 pi r 3 cube, 4 over 3 pi r cube, right? So, um, so for a particular radius, you can then use Monte Carlo to do your simulation. Estimate the volume of a sphere using, okay, simulation problem, simulate rolling two dice and estimate the probability that this sum is 7. You know, all of that, so you can try all this out. Let me know how helpful this is for you. And there's something else you'd like me to try out. Feel very free to let me know. If you have subscribed to the channel already, I thank you very much for doing that. If you have not, go ahead, subscribe, and let's have a nice time together. You could also go on to become a member of the channel by clicking on join. That gives you special privileges like being the first to see some videos before others, or you can even see some videos exclusively because you're a member of the channel. All right. You can, of course, ask for PDF copies of my notes. We can also hang out physically if you're ever in the same geographical location, or we can hang out online to discuss whatever interests you on the channel, like mathematics, data analysis, data science, machine learning, AI, and all of that. Also, don't forget to comment, like, share so that more people can have access to the great content I have going on here till I come your way again. Keep doing math right. Bye.